Hi everyone, and welcome to this next lecture, which deals with magnets and electromagnets. Now it may seem a little bit strange that we're talking about magnets. However, as you'll see as we go through, talking about magnetism and magnets is very important with our electronic circuits. And it's going to be a bit of a lead-in to when we get to talking about relays and also inductors in an electronic circuit. So first of all, here, this little guy is a magnet. If I get this little screw, so it's made of ferrous material, it's going to be able to get attracted to that magnet, and it actually stays there, gets held. If I put a whole heap of these together, I get effectively a bar magnet. Now I'm pretty sure that all of you guys watching this would have actually used a bar magnet, maybe just because it's fun to play with magnets, or maybe in school you actually did some lessons on them. But with a bar magnet, we've got what's called the north and the south pole. And I'll draw up a little something in just a moment. But one of these sides here would be the north and the other side would be the south. So if I get this piece of metal, so this screw again, and put it over here, you can see it easily attracts over there. Put it over here, same sort of thing, it attracts over there. What about if I put it to the middle? So I'll put it to the middle and I'll let go and see how it generally tends to want to go towards one of those poles. Even though I'm putting it towards the middle, it still wants to go to one of the poles. So what's happening there? Well, first of all, let's draw up a little magnet. So we're going to have a north and we're going to have a south pole. Now what we have with magnets is we talk about the lines of flux or the lines of force. So they're invisible lines, so you can't see any around this at the moment, yet they are there and we can interact with them, we can feel the effects of them. Now these lines of flux travel internally from south to north through the magnet, and then externally they go from north to south like this. So if we were to keep following these through, they'd go like that. Now a magnet that's not very strong, kind of like a fridge magnet, I mean they do the job, they actually stick to the fridge. However, they're not going to be anywhere near as strong as something like this, so it's not going to be able to pull this out of my finger like that. But if we're talking about a pretty weak fridge magnet, we'd represent that with just a few of these lines like that, spaced pretty far apart. If we were to get a stronger magnet, we'd represent that by having more lines of flux or more lines of force, and these lines would be more concentrated, they'd be drawn closer together. So what I'm getting at here is when we draw this on paper, the more lines you have there and the closer they are together, then the stronger the magnet is. Now the other thing I want you to notice is, so just like with my demonstration over here, we had the bar magnet and I tried to put this to the middle and it just kept tending to want to go to one of the poles. So going by what I said with those lines, the closer they are together, or the more that you have of them in one particular place, then the stronger the magnet is. So notice that the strength of a magnet doesn't just change from one magnet to another, it changes within one particular magnet itself. So where do you think it's going to be strongest with this magnet? Well, it's going to be at the poles, because if you notice at the poles, they're very, very concentrated. In fact, I should get yellow. So look at the pole there, look at the pole there. See how these are very concentrated right here. Very, very, very concentrated. Lots of lines very close together. Lots of lines very close together. But as you go away from the poles, they're actually going through the air in this case, and they're getting further apart, not as strong. So that's why the poles are the strongest. Now you may have seen another type of magnet, which is a horseshoe magnet. So if you were to get well, let's just pretend this is my magnet over here. If you were to get a bar magnet and then you were to get a really strong man and you bent it around, what are you going to make? Well, you'll make a, it's a really bad horseshoe magnet, but I guess you get the picture. So it's still going to have a north and a south pole in this case, and the lines of flux will do the same thing. They'll go from south to north internally, and then externally they'll go from north to south. So you'll keep getting them going like that effectively, and even in there. So I guess the good thing with making a magnet like that is you've got the two poles really close to each other, so you can effectively make a stronger magnet. Instead of having just one side attracting something and then the other side attracting something else, you can have them both working together. Alright. Let's just touch quickly on how a magnet would actually be made. So I can make this screw into a magnet. How would I do that? Well, if we have a little bit of a look inside this screw, you've got all these, so all these atoms are joined together, all their valence shell that are creating bonds, and put a whole heap of these atoms together, and they get called magnetic domains. So they all have a little bit of magnetism with all of them. So you can picture these as little magnets. But notice how I'm drawing these. They're all in random directions, which means their north and south poles are just all over the place. So the overall effect of this is they just cancel each other out, and there's really no magnetism at all. So this does not attract this. But what if we could do something to actually straighten out these magnetic domains so we can make them line up with each other? So they're all in a nice line. Well, that would actually create a magnet, and we can actually make magnets. So there's different ways of doing that. We can actually get this guy, and you can actually start rubbing this against that, and you can start to make these magnetic domains line up, and this could eventually become a magnet. Now there's another way we can do it, and I'll touch on that in just a moment, but what we want to get into now is electromagnets. So first of all, let's have a look at this piece of wire. If I was to get this piece of wire, the two ends of it, and connect it to a power supply, just like this, so here's my negative and positive, and then here's my piece of wire right here. We connect that between the two. There's going to be electrons flowing from the negative up here through to the positive. Now, something interesting happens when you do that. When you have current flow going through a conductor, a piece of wire, you actually get a magnetic field build up around that conductor at 90 degrees to the direction of current flow. So if I replace that piece of wire with my pen right here, those electrons, if they're traveling from down here up through here, so they're going in this direction, 90 degrees to that is going to be a magnetic field. So if we go there, 90 degrees to that is this way, so there'll be a magnetic field rotating either this way or this way around that pen or around that piece of wire. But how do we figure out which way the magnetic field is going? Well, that's where Fleming comes in. So we have Fleming's left-hand grasp rule, which applies to electron flow. If you're dealing with conventional current flow, you do use the right-hand rule. But all of my lectures are going to be dealing with electron flow. So, Fleming's left-hand grasp rule. So you get your two hands, figure out which one is left. In this case, it's this one, because it's got an L for me. So the left-hand grasp rule means I'm going to get my wire. Electrons are traveling from bottom up through the top. I'm going to grab my hand with my thumb pointing in the direction those electrons are flowing, so pointing up, and then I'm going to grab that wire with my hand. Now my fingers actually show me the direction the magnetic field is rotating. In this case, it's rotating in a clockwise direction as I look down on it. So as I look at this thing, it's actually rotating, what color, let's get purple, in this direction around it, and that's around every single part of that wire. Probably a better way to think of it is to rotate this so we're looking at it straight on. So if we rotate it so we're looking straight on, so I'll rotate it this way and I'll rotate it this way so we can get an idea of what's happening. In this case, we're going to use what's called dart notation. Now, with dart notation, let's have a look at the two instances. Let's say that the electrons are traveling from the camera through to me. With a dart, if someone, I hope nobody does this, but if someone was to throw a dart at me, what was this thing that I would see first? Well, I would see the point of the dart. So if it's coming towards me, I'll see the point. So if the electrons are traveling toward me, that's how I'm going to draw it. I see the point. Now if I turn it the other way and I throw it towards the dartboard, I'm going to see the actual flights at the back. So I'm going to represent that as an X. So that is away. So if the electrons are traveling away from me through the wire, that's how I draw it. So let's apply Fleming's left-hand grasp rule. So the first one I'll do is toward. So the electrons are traveling towards me. I get my left hand, my thumb pointing in the direction of those electrons, so it's coming towards me. I wrap my hand around, and this is the direction of the magnetic field that is built up. So it's actually going to be going this way around the wire. Let's do the opposite. So I rotate this around. Now the electrons are going away from me. I get my hand, my thumb pointing in the direction of those electrons, and my hand wraps around it this way, and notice that it's going in the opposite direction. So that's how we can figure out the direction this builds up. But, I mean, who really cares about that? Well, we'll get into that in just a moment. Let's get my piece of wire, turn on my power supply. So here's my positive and negative. I'm going to connect it up to this piece of wire. Don't worry, I know this creates a short circuit, but my power supply has a current limiter circuit. So I connect this up, and there we go. I get my screw, and there's a magnetic field rotating around this thing at the moment. We can't see it. Can we feel the effects of it? No. So that's doing nothing. Alright, so why did I just tell you about that then? Well, we can actually enhance the effect of this. So what I've done here is I've got that same piece of wire, just like this one, and I've got a screw, and I've wrapped it around. When I do that, I actually combine all of these little magnetic fields, put them in a tight space, so just like when we were talking about this before. So if we can get all of those in a tight space, we can enhance the effectiveness of that magnetic field and make it a stronger magnet. So exactly the same length of wire. I'm just going to connect it up to here and to here. And now we'll see if it does anything. So here's my screw. And you can see now it holds on. So it's not going to be as good as a magnet like this one, because this one will be able to pull it away from there, but it still does the job. It still has turned a non-magnet into a magnet. So how do we know where the north and south pole is when we do something like that? That is a good question. Okay, so let's draw up a little magnet. Sorry, a little screw. So let's pretend that's my screw there. And I'm just going to get my wire and wrap it around. So it comes around like this. Now what's actually happening with this when I connect it up to a power supply, let's go negative there, positive over this side, is those electrons are going to travel from negative up here, down around the back, up here, down around the back, up here, down around the back, and down through here to positive. So if we were to think a little bit about dart notation in this case, so I'm just going to make my circuit a little bit different so you can get a better idea. So what's happening here is we've got a wire coming up like that, and then it gets wrapped around again and again and again. And if you picture, it actually goes around the back down to here, around the back down to here, and down to here. So those electrons are flowing up this way, and then it's going to go down through, around the back, and then back towards us. So think about dart notation. It's going to be going through that way, so we're going to get an X there. It'll go around the back towards us at the bottom, so we get the dot coming through, dart notation. Back around this way in there, so we get an X. Around the back, we get a dot. Up through here, we get an X. So you notice all the dots end up being down the bottom, and all the X's up the top, and then we go down this way, so we're going from negative to positive. So let's have a look at what's going on here. The X is going up the top, the dots are down the bottom. Think about Fleming's left-hand grasp rule. So let's have a look up the top first. It's going away from me, so I need to put my thumb that way because it's going away. My fingers wrap around in this direction. So let's get a different color, let's go green. We're actually getting a magnetic field rotating this way through all of these. So just remember Fleming's left-hand grasp rule is the thing that's going to tell us this. So what about these dots down here? Well, down here it's coming towards us. So my thumb is coming towards me, my fingers wrap around in this direction. So we're actually going this way. Like that. Now, I'm just showing you these specific points just to to hopefully drive the point home. But this is actually happening at every single point along the wire. Now notice, because they're so close together, what actually happens is they start to feel the effects of each other, and they kind of morph together to provide or to give you an even stronger magnetic field. So if you follow these ones, these are all rotating in this direction. So we actually start to get a field that's going like this. So right through there. Unfortunately, I've drawn that too high. And then down the bottom here, they're coming this way, they're going out this way and in this way. So can you kind of see this is looking a lot like that original picture of this one. It's just the lines are going in the opposite direction. We've actually created effectively a bar magnet by doing this. So we've turned a humble screw into a bar magnet. So there's a couple of ways we can figure out the magnetic field. So first of all, if you have a look, the arrows are going this way. Internally, they're going from left to right. Now if you remember, I originally said here, internally, the lines of flux go from from south to north. Externally, they go from north to south. So have a look, internally, they're going from this way over to this way. They go from south to north. Therefore, we must have a south over this side with a north over this side. There's another way to figure it out, however. What we can do is use Fleming's left-hand grasp rule, but just a little bit differently. So again, grab your left hand. We're going to put our fingers over these coils of wire. So here's my magnet. We're going to put it over the coils of wire in the direction that those electrons are traveling through. So in this case, see, we've got X's up the top. That means it's going in with the X's, and then my fingers would wrap around it, and they'd all come through down the bottom, so they're coming back towards me. So that's how I'd wrap it around. My thumb is going to point to the direction of the north pole. So my thumb is pointing this way, so there's my north, and of course the south has to be the other side. How do we swap the north and south? Well, we could just rotate this whole thing, or we could swap the power supply. We could put positive over here, negative here. Now the electrons are all going in exactly the opposite direction. We're now going to get dots here, crosses down the bottom, everything swaps around, and now my hand would have to wrap around this way, giving me my north over this side. So that there is how we can make an electromagnet. Very important for when we're going to start to talk about inductors, which is going to come up in a later lecture, but also loads of applications that we use these in. For example, if you've seen at junkyards, they grab the big cars with these big magnets. They're electromagnets. So the guy driving that thing, he pushes the button, it activates the electromagnet. We have all these electrons traveling through. We get this big magnetic field, picks up the car, he releases the magnet, turns off the current, and it just drops it because it loses its magnetic field. We use them in relays. So in your car, when you flick the switch to turn on your headlights, that switch actually sends current going through a coil of wire, which activates a magnetic field. That magnetic field pulls down on this big piece of metal, which then completes the circuit to turn on your headlights. We use them in security doors. So you know those doors where you put in the buttons, beep, 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 beep. When you get the correct combination, the door unlocks. Well, the way that works is you put in the correct combination, it's going to activate an electromagnet. That electromagnet pulls the locking mechanism through so that it unlocks the door and you can open the door. Loads of uses, and we'll get into some more of these later. But not only that, we can actually use this type of stuff to generate electricity. And we'll have a look at that a little bit later as well. Alright, so for now that is it. Hopefully you got a lot out of this one. I'll write up some questions, you guys will do the questions, and then we'll continue on. Thanks for watching.